going to record a couple lectures on control beyond just proportional controllers. So we've learned how to use the root locus, adjust the gain, and then come up with a controller based on just a proportional gain. Remember, though, that we are stuck with things that, or that closed loop pole locations, I should say. Not just things, but closed loop pole locations that appear on the root locus. However, often we want to have performance that would require our closed loop poles be off the root locus. And that takes us beyond proportional design. So, using proportional design, the closed loop poles are restricted to the root locus. Often the root locus does not pass through the closed loop pole location specified by performance requirements, for instance, settling time. Therefore, design techniques can move the poles to desirable locations that we'll explore now. So we consider two classes of controller: proportional integral derivative, the familiar PID, and then proportional lead lag. So they're very similar. PID controllers use ideal integrators and differentiators, and therefore require active circuits for instantiation. Proportional lead lag controllers can be considered approximations of PID controllers. And these can be realized in passive circuits. So you can use capacitors and inductors, that type of thing. You don't require that they be powered by some external source. Like, so for a PID controller, you would require that you would have a like an op amp or something in there. So the approximations work pretty well. The lead lag, depending on your situation. We will build controllers incrementally by cascade compensation, which is illustrated in figure 6.2. So if you look at this figure, what we've got is our plant. Okay, so we've got our plant, our feedback transfer function, our output that we're trying to control, the command that we would like to have the output be like, and then we've got this controller. Okay, so we've learned how to design just for gain controllers, but compensators are what we'll use to augment that gain controller to give us performance other than what a gain controller can give us. So this is called cascade compensation, where we first will design a gain controller, and then we'll design a compensator, say C1, and then we'll design maybe another compensator, C2. So for instance, a PID controller, the way that we'll design them is we'll design a proportional controller, then we'll design an integral controller, and then we'll design a derivative controller. So proportionals first, then an integrator compensator, and then a derivative compensator. So these are the different compensators that we'll just concatenate then, or cascade them. So that's why it's called cascade compensation. So the compensators are those aspects of the controller that we cascade or link together in series. So that's the general program, how we'll proceed. I recommend reading this footnote. The idea is that we have this distinction between active and passive controllers. And when you talk about that, we're thinking about analog circuitry, right? So I said you can use inductors and capacitors, passive elements, to approximate the PID, so the active control of PID, so that would be with op amps. So both of these are continuous systems, thinking about analog circuits in terms of instantiation. However, most of the controllers that we create nowadays are digital controllers. So digital controllers are something that have become much cheaper in a lot of cases to implement, and they're more adaptable to new situations. When something changes, you can easily change the controller, whereas in an analog circuit, you would have to change the circuitry itself a lot of times, and that would be more difficult. So we are going to talk a lot about how to do this PID control and lag lead control, or lead lag control, and it's just really a little bit confusing, I think, when you think, well, we're just going to use digital control anyway, so is this even relevant? And fortunately, we can actually use this continuous time control techniques, these design techniques that we're going to develop here, for digital control as well. And the high analog to digital and digital to analog conversion rates that modern digital controllers give us allow us to essentially treat these systems as continuous in a lot of applications. So we can design things in a continuous way, and then we can convert it over to a digital control environment, so for implementation. And the details of that, I would recommend you take the embedded computing course, because we go through some of the details of how to do that. There's a lot involved in it, but the controller design aspect is really not that much different than what we're talking about here. So the same principles are going to apply in that case. You just have to add a couple layers of abstraction. So anyways, that was just a little sidebar on continuous versus discrete control. So the analog stuff is still valuable even if we end up using a digital controller. At the end of the day, the analog design is typically very valid still. So that's the general program. So we will now go ahead and introduce the next topic, which is going to be PI control.